Start with some questions from homeworks. Does anybody have any questions from 1 through 16 that they wanted to talk about? Happy to do them. Going once, going twice. Okay, maybe next time. Today, we're going to be looking at 15.2. And in 15.2, we're going to be making exponential and logistic models. So in the previous section, we used these exponential and logistic models to answer questions. Today, in this section, we're going to actually be writing our own models from like situations. So we'll start with this first definition, which is just the exponential population model. It states that if a population P is changing at a constant percentage rate R for every T units of time, whether those be days, months, or years, then the exponential population model can be given by the equation P of T equals P naught times the quantity 1 plus R over 100 all to the T, where P naught is the initial population, R is the percentage rate of change, and T is the time. So if you look at this population model, you should notice this is just like the A times B to the X population model, where like the P naught is our A, and the 1 plus R over 100 is like our B, and then the T is like our X, right? So this is still just like an exponential model, just like we saw last time. So the same rules apply. So let's look at some or at least the same rules apply in regard to like growth and decay. So let's take a look at some examples here. So here's a couple of population models. If I look at the model for part A, is that growth or decay, and why? If I look at part A, P of T equals 12,587 times 1.0384 to the T. Is that growth or decay? And then how did you know? Who remembers from last time? I'll give you a hint. We have to look at the value for B. What am I comparing that value to? Go ahead, guys. It is growth. How do I know it's growth? Because it's greater than 1. Yes. Take care. Good luck, fellas. Score some goals or stop some goals, depending on where you play. All right. Part B, then. What is part B? Is that growth or decay? What are we comparing this? What number are we comparing the B to? It's the same as part A. What did we compare it to? 1 is correct. Notice here that this number is less than 1, so what does that tell us? That it's decay. That fact is something that you'll want to remember. Now there's a second part to this question. It says, and then find the constant rate of decay. So we need to, and the constant rate of decay, what does that mean? That's the value for R in our population model equation. So just a moment ago, we talked about how that 1 plus R over 100 was the same as the B. Everybody's okay there? So I'll plug in my value for B that I got by looking at my equation. And I'm going to solve that now for R. First step would be to, what should I do first? Oof, this is like Algebra 1. We're not even. Subtract 1, thank you. Next thing I should do is multiply by 100. And that's now a percentage. So that's my value for R. How would I do part B? I do it the exact same way. But since this is decay, what kind of number am I expecting to get for my value of R? Negative, yeah, very good. So again, we'll start by subtracting 1 from both sides. Just like we did before, and then multiply through by 100. How do you guys feel about this? It's no big deal, right? We're just using the formula and doing some Algebra 1 level solving. You know what I'm saying? Let's do another example. So here, this one says, determine the population model with an initial value of 15, increasing at a constant rate of 6% every year. So population model, well, that tells me that I should be using my equation P of t equals P naught plus, or P naught times 1 plus R over 100 to the t. Initial value of 15, well, that tells me P naught is 15. Increasing tells me that it's positive. A constant rate of 6% tells me R is going to be positive 6. And then the last thing we have to do is decide the unit for t. Well, it says it wants this every year, so let's just make t be in years. So let's plug the stuff in. P naught was 15. R is 6. If I do 1 plus 6 over 100, that's 1.06. There's my population model, and I should probably say t is in years, since we're given the choice of what unit of time we want to make t in. How's that feel for you guys? Is that okay? Oh boy, it is totally a Friday, huh? Is this a contest you guys are having to see who can say the least? So far, it's a tie for first. All right, let's do another one. So determine the population model with the initial value of 15, increasing at a constant rate of 6% every 6 months. This is almost identical to the situations before, right? I know from population model, we're going to be doing this. It says the initial value is 15. So I know that P naught is 15. Increasing at a constant rate of 6% tells me R is 6. But the place that's different than the previous problem is that it says that this is happening every 6 months. So we need to decide what unit of time we want to make our t in, and then we'll have to do some adjustment here. What unit of time do you want to use for t? There's probably 2 reasonable choices. What? You could do t as in months, or you could do t in. Well, if the unit is 6 months, I would do years or months, right? Depending on what you wanted to do. If I do t in years, we'll do that one first. And then we'll do the or, and we'll do t in months. So let me just kind of move that in here, and then I'll write something down in a second. All right, so if t is in years, how often does 6 months occur in 1 year? Twice. So instead of writing t here, I'm going to write 2t. Because that increase is going to happen twice inside of 1 year because it's happening every 6 months. Everybody okay there? Okay. How often does 6 months happen inside of 1 month? Well, not exactly 0. It's like 1/6, right? I get 1/6 of a 6-month period in 1 month. Everybody agree with that? So instead of writing t, I'm going to write t over 6. And then if I simplify again, I could write my answer like this, or like this. Either one would be acceptable. Everybody's okay with how to deal with a varying time period? You have a little bit of choice as to like what unit you want to use, but you have to make an adjustment for how often that increase is happening or decrease is happening, right? And as you guys see that it's usually easier to think about picking your unit of time to be bigger than whatever the increase or decrease is happening in, but that's not always reasonable. All right, let's do another example. Okay. Here it says, suppose a colony of 120 bacteria is put into a petri dish and the culture doubles every 3 hours. And then we're told to predict how long it would take for there to be 400,000 bacteria. So we have a colony of bacteria, so that's going to be a population model. So let's start there. I'm told we start with 120 bacteria. So that's my P naught. But I don't read an R here because it doesn't say increases at a constant rate of, right? So what is how am I going to get the R out of this? What words are telling me the value for R? Take a read through again if you need to. Think about it for a second. What words are telling me the value for R? It's the word doubles. What percentage change is going to result in a doubling? Somebody, please, give me a something. What percentage change results in a doubling? Even if you're wrong, that's okay. 50. So if you have $2 and we give a 50% change, so 50% of $2 is $1, you'd end up with $3. That's not doubled, okay? That's fine. So you said 200, so 200% of $2 is $4, 2 plus 4 is 6, that's not a double. 100% of $2 is $2, $2 plus $2 is $4, that's the percentage we're looking for, is 100%. Is everybody okay with how I thought that through? Yeah. Okay. Again, it's okay to be wrong. It's what I expected. Nobody gets this right on the first try. Seriously. Every year I do this. Even the honors kids screw that up. Don't feel bad. Okay. The last thing we need to do is pick a unit for T. So what unit do we want to use T in? What unit of time? Years, hours, days, months, seconds, weeks? What do you want to do? To me, there's an obvious choice. Hours, I would agree. Why did you pick hours? Yeah, because it's happening every 3 hours. Okay, how many 3-hour segments happen inside of 1 hour? How much of that 3-hour segment happens inside of 1 hour? 1/3 of it. So we're going to write T over 3. You guys good with that? Maybe that's the better way to phrase it. You got the idea there much quicker. Okay, if I do a simplify, 1 plus 100 over 100 is 2. Hey, there's that doubling that they're talking about. So there's my model. But notice it asks predict, there's a second question here. Predict how long it would take for there to be 400,000 bacteria. How long means it's going to be asking for a t, for a time, right? So what I'm going to do is I'm going to solve my model P of t equal to 400,000. How am I going to do that? I'm going to use the calculator. Again, we don't know how to algebraically solve these things yet. So for the time being, we are stuck just kind of typing this into our calculator. Well, 1 plus 100 over 100 turned into 2. So I went and typed in my population model, and I'm typing 400,000. I'll select a window. I don't really know how long this is going to take. It might take kind of a long time. I don't know, like 100 minutes maybe? Doubling is a lot. The population, I know I start at 120, so my Y min, I'll just pick a little bit less than that, nice round number of 0. And I know I have to get over 500,000, so maybe I'll pick my max at 500,000. I say I have to get to 400,000, so I'll pick something a little bigger than that, 500,000. And let's do that. So there's, whoa, doubling is steep, man. Look at that, how steep that got. There's my intersection. So second, trace, use the intersect command. And since I have only 2 things graphed, I just can press enter 3 times. And I get about 35.11 hours. Right? Because we said T was in hours. Everybody okay there? Still doing good? Another common situation is something called radioactive decay. So in chemistry, like, you guys know what an isotope is? Right? Like, elements have a fixed number of protons and electrons, but the number of neutrons can vary from element to element. Some elements have lots of possible assignments of neutrons. We call those elements, or those different assignments of neutrons for one element, an isotope. Some of these assignments of neutrons make that element very unstable. In an effort to get to a more stable configuration, that element will eject some particles from its nucleus, neutrons and protons. That process is radiation, that act of releasing those particles from its nuclei. The process of going from an unstable isotopic configuration, ejecting some radiation and turning it into a new element that has a different number of protons and neutrons that is more stable, is called radioactive decay. We measure radioactive decay by the amount of time it takes for a sample of an isotope, for half of it to change into that more stable other element. So the big takeaway here is, if you're looking at a radioactive decay situation, the R value is always going to be the same. What is that R value going to be for a half-life? Somebody take a stab, please. The R value for a half-life. What percentage change is going to move you from 2 to 1? Where your quantity is decreased by half. Somebody take a stab at it. What? 25? 25 is not correct. 25% change would be from 1 or from 2 would go to 2.5. Because 25% of 2 is 0.5. You add that to 2 and you get 2.5. Yes.
So negative.
Negative 25?
No.
No.
Negative 50.
Negative 50. 50% of 2 is 1. 2 minus 1 is 1. That's what you're looking for. So the big takeaway here is that this is going to work just like our population model. But as soon as I see half-life, I'm just going to know that R is negative 50%. That is the takeaway. Otherwise, these are going to work exactly the same as our population models that we just got done talking about. So nothing really new, just that we recognize that a half-life means that R is negative 50%. Okay. So let's say, suppose that the half-life of a certain radioactive substance is 35 days. So it's a radioactive situation, so I'm going to start by writing this population model. And you have 10 grams of the substance initially. Find the time it would take for there to be only 1 gram remaining. So let's write our model first. What should my P naught be? That's the initial amount of substance. Can somebody tell me what the P naught should be for this problem? 10, very good. Right, it says you have 10 grams of the substance initially. What should the value for R be? Who can tell me that? What should the value for R be? Half-life. What? Close. Negative 50. Always negative 50 if it's a half-life. Every single problem. Now we should pick a unit of time for our T. What should we measure T in? What unit of time? Again, I think there's an obvious choice, days. So how much of our half-life is accomplished in 1 day if it takes 35 days? Our half-life is 35 days long. How much of that half-life is accomplished in 1 day? 1/35, right? Everybody's okay with that? So I'll write T over 35. So let's just clean this up a little bit. 1 plus negative 50 over 100 is 1/2. Hey, look, there's that half-life. So there's our model for the radioactive decay. And then the last part says find the time it would take for their 1 gram to be remaining. So there it's asking for a value of T. For 1 gram tells me that for when P of T is equal to 1. How am I going to solve that equation? Going to use my calculator. So I'm going to go ahead and type in my new model. And the amount that it has to equal is just 1. Now I'm going to set my window. So let's think about this real quick here. To get from 10 down to 1, if I'm counting by halves, half of 10 is 5. That's 1 half-life. Half of 5 is 2.5. That's 2 half-lives. Half of 2.5 is 1.5. That's 3 half-lives. Half of 1.5 is like 0.625. That's 4 half-lives. Everybody's okay with that? So somewhere in between 3 and 4 half-lives, we would have hit 1 gram. Is everybody okay with that? Oh. So why did I do that little thought process in my head? Because it's going to help me pick my scale for X. 1 half-life is 35 days, so 4 half-lives would be 210 days. So I'm going to pick something around that. I'm going to pick 200 just because it's a nice round number. Go by 20s maybe. Now the Y minimum, because it's a decay, for any decay, the minimum should be 0, right? And the maximum, well, that's going to be what we started with. So 10. I'll go by 1s. And let's hit graph. So there's my exponential decay. There's my line y equals 1. There's my intersection. Oh, lovely. Second trace, intersect command, enter, enter, enter. And I get about 116.3 for t. What do you guys think? So far, so good? The solving process is the same solving process we used in the previous homeworks. So it's still just using your calculator. Again, for the most part, this should be fairly straightforward. There's not a lot of complicated mathematics going on, but you definitely need to know your calculator. You definitely have to know your models and know the vocabulary so you can get this stuff set up. But the process is not long and arduous, right? This is pretty straightforward. All right, I got one more example for you, and we're going to call it a day. Sound good to you guys? Yes. I hope it did. All right. This is a logistic example. I don't think I have any problems where I'd ask you to write your own logistic model. It just would be problems like this where you're using the logistic. So it says you start a bunny petting zoo. You determine that the population of bunnies on your farm can be modeled by the equation B of t equals yada, 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 where t is measured in years. How many bunnies do you have initially? So what would the t be for initially? What value of t is initially mean? Somebody take a guess for me. What does the word initially mean in the English language? To start with. Great. What would the starting time be? Just thinking logically. Well, a unit. It has to be a number, right? 0, right? What initially would be before anything has started. The first time that you can have is like 0. Everybody's okay with that? So all I'm going to do is b of 0. That just means I'm going to be plugging 0 into that equation up there. I'm just going to do that on my calculator in a minute. I'm going to go on and do the rest of this first, and then I'll come back and type that stuff in, so I'm not toggling back and forth and back and forth and back and forth between my calculator. Part B says, what is the maximum sustainable population of the bunnies on your farm? Well, what type of logistic model is this? Is this growth or decay? What do we have to look at to tell? Since this is the model with the E in it, what I'm looking at is the value for K. Since that is negative, it tells me that this is growth. So the maximum for that is Y equals C. And C is just that number in the numerator. So I get 800 bunnies without even really doing any calculation, right? It was just, I recognized that it was a logistic model, that it was growth, and that the maximum sustainable population for a logistic model is just the numerator. That's it. Oh, that's nice. And the last one says, how long, so we're looking for a T there, because T is time, will it take for you to have 500 bunnies? Well, I'm just going to be solving B of T then equal to 500. How am I going to do that? Once again, just going to type it into my calculator and let the calculator do the heavy lifting there. So we'll fire up the old calculator here. So alpha y equals, type in that guy. I like using the fraction command with these logistic models. It's an awful big pain in the tuchus, to get this in there the right way without that. So I definitely would like to use it if I can. So there's my exponential typed in, or my logistic model typed in. And then I'm going to be solving that for 500 here. But before I do that, let's answer part A. So I'm just going to do vars, y-vars, function y1 of 0. That's just going to plug 0 into B of t for me. And I get 8. So initially I must have had 8 cute little bunnies. Just a little bunny. Let's find out how long it took for those 8 little bunnies to turn into 500 bunnies. So here I'm going to graph this. T is in years. Bunnies are renowned for their ability to reproduce quickly. I don't know. I don't have any good guess here, but 50 seems like a sufficiently big number. The y minimum, well, I'm going to start at 0, and the maximum is 800. So I'll do that, go by hundreds or something, hit graph. So there's my S-curve for my population model. There's the line 500. Here's my intersection. Second, trace, intersect command, enter, 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 and I get about 10.2. So after 10.2 years, those 8 cute little bunnies became 500 cute little bunnies. Those bunnies were getting busy. It's a lot of reproducing. Any questions so far? What do you guys think? So excited today. Your amount of interaction and participation has been awe-inspiring. So for this set, you guys should be able to do 17 through 36. Is that due this Sunday? No, man. It's due next Sunday. What's due this Sunday? Just 1 through 16. Okay? I'm done for today. So get your stuff out. Be productive. Get some stuff done so you can have a relaxing weekend. Knock out this homework. I know some of us are probably busy with athletics and who knows what else. Save yourself some headache. Get your math done now. Be productive. You got a solid 40 minutes. You can probably bang through 1 through 16 if you're motivated. Get crack-a-lackin', folks.
We're seniors, it's still good. That's